This video will cover Chapter 9 of the textbook, and this is part 1. And we're going to be talking about modeling the population proportion. I want to start off with the fair coin hypothesis again. And this time we're going to model the situation by considering the sample proportion. The question's the same. Is the Super Bowl coin 28? Is the Super Bowl 28 coin a fair coin? The null assumption is that the coin is fair. The alternate is that the coin is not fair. And again, we translate the theory into a statistical hypothesis, or the situation into a statistical hypothesis, just like we did before. And we end up with the more mathematical hypothesis that the null being that the true proportion of heads, since we're looking specifically at heads in this example, we're going to assume that the true proportion, P, is 50%. That would be a fair coin. And the alternate is the coin is not fair, meaning that the true proportion is something other than 50%. And again, just like before when we discussed this, thinking in terms of the binomial distribution, same scenario. Suppose we get permission to flip the Super Bowl coin 10 times, same conditions, etc. And this time we're going to define the variable as the number of heads, again as before, and we're going to use the same observed value, x equals 7. And the question is the same, is this result rare and unusual? And again, we need a p-value. So what we're going to look at in this video is another way to calculate this p-value. So when we go back and we look at the original distribution for the null, again, thinking about this in terms of the variable x now as the independent variable. And again, just to be clear here, on the domain of x, since we're flipping the coin 10 times, the domain is the set of whole numbers, 0, 1, 2, up to 10. So that's the domain. But what we're going to do is, instead of looking at x, we're going to transform x by dividing it by n. And what that's going to give us is a sample proportion. And it's really important to understand, first of all, that p hat is a variable. P hat is a statistic. It estimates p. And also, a variable, all statistics are variables. And being a variable, then it has a distribution. So in this example, we're going to take the original domain for the problem. We're going to transform that domain using the formula p hat, the sample proportion, equals the number of heads over 10 in this case. And I get a different domain, a new domain, that are really percentages, right? So we have the possibility that we get no heads, meaning 0% is the estimate for the true proportion. 1 head means we have 10% heads, etc., all the way down to 10 out of 10, which would be 100% heads. And again, when we look at the distribution for p hat now, okay, I want to label these axes. The x-axis here is x, as before. When we do this transformation, though, the x-axis now becomes the p hat axis. But the probabilities stay the same. And so the general shape of the histogram doesn't change at all. And so really, again, all we've done is we've changed and transformed the domain from one variable to another, from x to p hat. Now, the shape of this particular curve, let me go back a slide here. So the shape of this particular curve looks very much like a bell curve. In other words, it almost looks like we should be able to superimpose. Let me change my pointer color here so it'll show up. It looks like we might be able to, model this situation with a normal curve. Now there is a mathematical problem that we have to deal with, and it's rather important, okay? P hat is a discrete variable. there are a finite number of elements in p hat's domain, okay? Therefore, p hat is based on a binomial random variable. So p hat's, one way to think about it is p hat's natural distribution is binomial. Okay, and so since it's discrete and specifically binomial, then the heights of the bars, the actual heights, represent the individual probability values for each p hat. So one of the issues that we have to deal with if we're going to model this with a normal curve is, and especially I want to compare the normal curve to this graph, is I need to go from the heights of these bars being the probabilities to the actual areas of the bars being probabilities. And that's just a rescaling process. Since the base for each one of these rectangles is 0.1, if I multiply the heights by 10, then the area becomes the probability. And so what I've done in this next slide is I've rescaled the graph so then now the probabilities are actually the areas under the curve. And what I've done is I've superimposed a particular normal curve, and I happen to know which one fits this situation. Of course, from experience and from, you know, I've been teaching statistics for a while, so I know the formula. And what I'm doing over here is I'm using p hat's approximate distribution. And it turns out, and we're going to talk specifically about this in a later slide, but it turns out that for the fair coin model, if the sample size is large enough, that we can model p hat effectively using a normal distribution with a mean of 0.5. That's the expected value for p hat, and then this measure of variability, which is a formulaic kind of a thing that we're going to use. And what I end up with is the following normal curve, which looks like it fits pretty well. However, all right, and let me say this a couple of different things here. All right, so first of all, let me back up for a second. I want to point out something here. So our observed value before, and still that we're going to use is x equals 7. And that means p hat from that observed value is 7 over 10, or 0.7. So if I go up here now to my graph, and since I've converted from the heights of the bars being the probabilities to the areas of the bars being probabilities, now I can actually shade the p-value. I'll do it on this graph as follows. The p-value is chance of getting the observed value, that's this area, plus the chance of getting all the more extreme values, and those are all those areas, right? And since it's a two-sided direction of extreme, then we got to look symmetrically. We have to look at the other side of the distribution as well and recognize that all of these bars, the areas of all these bars from 0.3 to the left would also be shaded. And that would represent the actual p-value. And in fact, this particular histogram was being generated using binomial 10.5. So this histogram represents the binomial 10.5 discrete probability distribution. Now, what we're going to do, though, is we're going to approximate this area, or this cumulative area now, using the normal distribution. And again, I'll give you this formula in a few minutes here, but I'll write it down. So what we're going to end up doing is we're going to look at, and again, we have to remember this domain for the normal distribution. What is the domain for for any normal function, the domain is the set of all real numbers. So it's a continuous distribution. Okay, and so let me just be really clear about this here. So the domain for the binomial situation is 0, 0.1, because I'm modeling p hat, 0.2, ... up to 1. And so there are 11 elements in the domain for the binomial distribution, but there are an uncountably infinite number of elements in the domain of the normal distribution. So what ends up happening is we're going to use the calculator to find the area under the normal curve starting at 0.7, which is the observed value, and going all the way out to positive infinity. Of course, we're gonna use positive E99 out here for that very large number, upper limit. And then we're also going to find, since it's a two-tail direction of extreme, we're going to also use the area on the left side, And again, because of symmetry, those areas are going to be equal. Now, one of the things that I want to point out that's really important here is the idea that the using the normal curve is going to have error. In fact, the error we can see, it's going to be this part of the 0.7 rectangle, and it's going to be this part of the 0.8 rectangle. It's a little bit here for 0.9. And also it's going to be this area right here and this area right here. So all of those areas are going to represent errors. Now, the one nice thing about how we're doing this, though, in especially again in the two-tail case, is that on the on the right side, we're that's not correct. We're underestimating. All right, because the normal curve is kind of clipping off the top part. So the area under the curve is going to be smaller than the area that would be in these rectangles. And then on the left side, the normal curve is overestimating. So there is a tendency in the two-tail case for these errors to kind of cancel each other out, and that's actually a good thing. But not in the one-tail case. See, if we were only doing, instead of the particular null and alternate we were working on, if the actual alternate changed and we were talking about a different theory, say where where p is greater than 0.5 in the alternate, that would be a right tail direction of extreme. Our estimate would be an underestimate, and we wouldn't have that kind of canceling out effect. In any case, I wanted to make it very clear that the normal distribution is the one that approximates the probabilities for p hat. So it's p hat's approximate distribution, and the binomial is p hat's actual distribution. Okay, so take 2 on the Super Bowl coin. So how can we find this p-value using the normal distribution? Because again, that's really the goal that we have, is to figure out what this p-value is. So let's just review. So anytime we need to calculate a p-value, we need the following 3 things. We need the null distribution. Okay, and we're going to, in this case, we're going to use the normal 0.5, square root of 0.5 times 0.5 over 10 distribution. We need direction of extreme. And since the alternate assumption is that p is not equal to 0.5, this means we have a two-sided direction of extreme. And then finally, we need an observed value. And in this case, the observed value is p hat, which is equal to 0.7. So the area that we're going to use, again, to estimate this p-value is the area under this normal curve to the right of 0.7 and the area under the normal curve to the left of 0.3. So on the TI, what we're going to do is type in, and again, there's a couple of different ways to do this. Let me do it the long way, and then I'll show you the short way too. So one way we could do is just say normal CDF negative E99, comma 0.3, comma 0.5, which is mu, comma square root of 0.5 times 0.5 over 10 plus normal CDF of 0.7 E99, this is the right tail area, same, of course, same mean, same standard deviation. Now, due to the fact that we're using the Farrakhan model or the balanced model, it turns out that we could find either one of these two areas, the left area or the right area, and just multiply that by 2. And that's because of the symmetry of the normal distribution. So let's calculate the p-value in this alternative way. Let's see, so let me clear this out. All right, so what do I need to do? I need to go second vars, choose normal CDF. We'll find the left area, negative, the left tail area, E99. I'm going to go up to 0.3, mean is 0.5, and the standard deviation is the square root of 0.5 times 0.5 divided by 10, close the parentheses. So that's the left tail area, and I multiply that by 2, and I get the estimate, my estimate for the p-value, about 21%. So again, there's definitely some error here because the p-value I got using the binomial was more like, if I remember right, more like, I believe, 34%. But still, we're going to be rejecting the null hypothesis in this, or I'm sorry, failing to reject the null hypothesis in this case. So the decision would be the same. Let's call that let's call it 0.2059. So the p-value in this case is approximately 0.2059. So again, the conclusion, the decisions to do not reject, the conclusion would be I'll just be brief. No statistical evidence that the coin is not fair. So that would be our conclusion in a nutshell. Same conclusion as before, which is good. Okay, so now let's talk about yet a different way to look at this hypothesis test. And again, we're going to let P represent the proportion of elements in a large population. So P is a parameter, it's the population proportion. It's got some characteristic. If a random sample size n is taken from my population, and here's something we haven't talked about yet, okay? If n is sufficiently large, let me discuss this for a moment. So where the errors are happening here are in these corners of the rectangles that are being chopped off, and in these gaps above the other rectangles on the other side. Now, this is, again, let me say it like this. So there's a test that we have to do for sample size. And really, the test are some conditions that have to be met. Turns out that the particular example I've just done with the superpole coin is the smallest sample size that I could possibly use the normal distribution for. Notice in this case, one of the conditions that needs to be met is n times p is greater than or equal to 5. That's a sample size condition. It's also got to be true that n times 1 minus p is greater than or equal to 5. Turns out in this case, p and 1 minus p are both the same, which is 0.5. And obviously 10 times 0.5 is 5. So we're right at the sample size threshold where we could no longer use the normal distribution to model the situation. And again, it's because we have fairly substantial errors happening here between the normal curve and the actual areas of the rectangles, which would be p hat's natural distribution. So that's the sufficiently large part that's being alluded to in the definition of the sampling distribution here. But what we say is, if the sample size is sufficiently large, then we can model p hat approximately using the normal distribution. What that allows us to do is standardize the variable. So yet again, another z transformation for a different variable. When we were modeling x bar, okay, then the z transformation that we used was x bar minus mu divided by sigma over the square root of n. That's modeling the sample mean. In this example, we're not modeling means, we're modeling sample proportions. So the z transformation here involves the proportions. But notice it's the difference between the statistic and the hypothesized parameter divided by a measure of variability. And that is what the z transformation is always about. And that's why we call it a standard score. So z is a standard normal variable. It's the n01, normal distribution, mean 0, standard deviation 1. That is the standard normal distribution. So it turns out now that if we have a large enough sample size, since we can model p hat with a normal distribution approximately, then we can do the z transformation. So what ends up happening now, again, is that we take our sample proportion, calculate a z-score, and then we find the area under the z distribution. So again, here's where my interest in your labeling these axes becomes really important, because when I put a p hat here, I'm using either the binomial or I'm using the normal centered at 0.5. When I label with z, I'm talking about the standard normal distribution, which of course is always balanced at 0. And so what we're going to be able to do when we, whoops, hold on, sorry, let me go back here. When we go back and think about the Super Bowl coin situation, what I could do is come up with a z-score. Now the p hat was 70%, the hypothesized proportion was 50%, and the standard, the measure of variability was 0.5 times 0.5 divided by 10. So this is 0.2 divided by the square root of 0.5 times 0.5 divided by 10. I'm getting my calculator out. I haven't done this ahead of time. Let me calculate this. So I got 0.2 divided by square root 0.25 divided by 10. And z-score value I'm getting is about, excuse me, it's about 1.265. And so what I would do now to calculate the p-value under this situation is I would go up here to about 1.265, and the area One thing I want you to notice here that's important is that the area, see the p-value we found before was this area, right, to the right. So 0.7 is transformed to this z-score value. The area over here on the left that I'm shading is equivalent to the area over here. I'm sorry, I said left, I meant right. The area over here on the right that I'm shading is equivalent to the area over here on the right that I'm shading. And then, of course, due to the symmetry, we'd also need to look at the area to the left of negative 1.265. So another way, yet another way to calculate the p-value is to do the z transformation and then do the normal CDF calculation. Again, if I did it in two parts, I'd find the left area with negative E99 up to the left-hand z value over here, and 0, 1 are the mean and standard deviation, and then I could do the right area. I could also multiply by 2. Okay, so let's do that. Let's confirm that we're getting the same area. So this time, again, I'm going to do a shortcut here. I'm just going to do one of the two areas and double it. So I'll do the left area, negative E99 up to negative 1.265. And it turns out the default setting for normal CDF is standard normal. So again, I'm getting the same p-value, approximately the same p-value as before. There is some round-off error here because the z-score value, I actually rounded off to the third decimal place. So if you notice, I have accuracy up to the third decimal place where I rounded to, and then I'm starting to diverge away at the fourth. But again, that is very minor, so it's plenty close enough for decision-making purposes. All right. Okay, so then there's one other thing I wanted to demonstrate to everybody. Now, one of the nice things about doing the z transformation here, and considering the z distribution rather than p hat's approximate normal distribution like we did over here, is that we can actually create, or could create, a universal kind of hypothesis test for proportions. So if you go to your calculator and press stat and go to tests, what you'll find is choice 5 is the one proportion z-test. If I choose 5, it's going to ask me some questions. What's the hypothesized population proportion? This is the fair coin model, so that would be 50%. The observed value, the x value, is 7. N is 10. Two-sided direction of extreme. So now I'll go down to calculate. Here's my p-value. There's the z-score. There's the p-value. There's p-hat. So all of that's calculated for us. It's all automated on the calculator. Let's take a look at another example. And this is back to the ESP problem. So now we're going to do an experiment. This is a different experiment, I believe, because we're drawing 96 cards this time. And we're going to do it one by one with replacement. That's important because now it's binomial. Each of the probabilities is the same and independent of each other. So that's important. From well shuffle ordinary deck of cards. Subject's asked to guess the suit of the card. It's 4 possible choices. Could be spades, hearts, diamonds, or clubs. Wish to test the null hypothesis the subject's only guessing, doesn't have ESP, against the one-sided alternative that the subject has ESP. Let P represent the population proportion of correct responses if this experiment were repeated many times. Think about what the value of P should be if the subject is only guessing and does not have ESP, and what the direction should be for values of P if the subject does have ESP. Use the following outline. Okay, so First thing we're asked for here is the null hypothesis. So this is the guesser hypothesis, which means that the true proportion of correct guesses should be 1/4 or 0.25. The alternate's the theory. That's what I'm calling the ESPers hypothesis. And that's that the true proportion is greater than 0.25. So if we find significant evidence that the true proportion is greater than 25%, then we would want to reject the null hypothesis and conclude that we found evidence that the person's using an extrasensory perception. That means we have a one-sided direction of scream, and it's to the right. So now what I've done is I have created a histogram for p hat's binomial. So p hat's natural distribution for this example is binomial. N is 96, p is 0.25. Now, if you look at this histogram, if you don't look at it closely, it would look like it's really nice and symmetric, and it is pretty symmetric. But if you look at it closely, you'll see that it's just slightly skewed. It's just slightly skewed to the right, in fact. But when I magnify, when I actually make my graph, when I restrict the domain of my graph, right, to the actual part of the graph that has some probability, and one of the things I see with this graph is that as I come down, as the histogram bars come down, the probabilities get really small. I mean, these probabilities out here are very small. This is very small probability. So all the action here is in a much narrower range of p hat values. So I've narrowed in on that. Now, what you see though is that when you get in here to where the actual probability is, the curve's still looking really smooth. Now, this particular example really does, this is a really fairly large sample. It's plenty large to use the normal distribution estimation. Again, if I take, well, I'm going to approximate, I mean, we've got 96. So if I call it 100 times 0.25, that would be 25. So 96 times 0.25 is going to be plenty big. It's definitely going to be bigger than 5. So I don't have any sample size issues here to worry about. So let's get down here to the results. So p hat is 35 out of 96. That's the actual p hat value that we're going to use. And that is approximately, I'm going to call that about 0.365. So now, instead of modeling this with let me write down actually what this distribution is. So the normal distribution here is normal, the mean of 0.25, and a standard deviation of 0.25 times 0.75 divided by 96. So that's actually the normal distribution here that we would approximate p hat with. The way we're going to do the problem here is by going straight for the z transformation. And so what do we need to do here is take our p hat value. Again, I'm going to round this off, so I'll have some round off errors. So we got about 0.365 minus 0.25. This is going to be divided by the square root of 0.25 times 0.75. And by the way, that's 1 minus p. And that's going to be divided by 96. So if I do that calculation, I'm getting a z-score value of approximately 2.602. So now the model, the distribution we're going to use is z distribution. That's standard normal. So the curve is centered at 0. Standard deviation is 1. So I can label the z-axis accordingly. 2.6 is right about here, 2.602. So what I need to do is to find the area. So again, my direction of extreme is one-sided to the right in this example. So I need to find it. So the p-value is going to be calculated by hand. We would calculate the p-value using normal CDF. Again, standard normal is the default, so I'm not gonna this time I won't type that in. So let's see, I'm gonna type this into my calculator, 2.602 399. So the p-value I'm getting is about 0.0046. And 0.0046 is less than 0.05, which is the level of significance. And that implies we should reject the null hypothesis in favor of the alternate. So we got statistically significant evidence that the subject is ESPing rather than just guessing. All right, now let's look at the formalized, what we call the z-test for a population proportion. So when we apply the one sample z-test for proportions, or one proportion z-test, if we want to test a hypothesis about a population proportion, the null hypothesis is that p is equal to p naught. P naught is the hypothesized value for p. The alternative hypothesis provides the direction of extreme for the test. The hypotheses are statements about the population proportion and not the sample proportion. Statistical hypotheses are always about the population, and they always are about the parameter values from the population. Sample proportion is the statistic that estimates the population proportion. Now, the data are assumed to be a random sample of size n from the population, so there you have the randomness assumption again, always there for all of our hypothesis tests and statistics. It's always one of the key assumptions. N is large, and here are the specific sample size criteria. N times the hypothesized proportion has to be greater than 5, and n times 1 minus that proportion has to be bigger than 5 as well. Calculate the z-score, and the distribution of the variable is approximately standard normal. Test statistics same no matter how the alternative hypothesis is expressed. Let's take a look at another example. Suppose that the unemployment rate in the United States is about 5%. Mayor would like to determine if the unemployment rate for a city is higher than that for the United States. So we got a random sample of 2,000 adults, and the observed value is 125. Now, first thing we are asked to do here is to translate this problem into a null and alternative hypothesis. So we're going to assume that the particular city has the same population proportion against the theory that the proportion is actually higher. So the hypothesis tells us that the direction of extreme is one side to the right. So the next thing we're asked to do is to calculate the value of the test statistic. So what the problem is referring to here is this z-score value. So we're going to have the p hat value, which is 125. Make a note of that. So p hat is 125 out of 2,000. Or about 6.25%. So the formula we're going to use here is p hat minus p naught divided by a square root of p times 1 minus p over n. And so in this case, it's 0.0625 minus 0.05 divided by the square root, and this is 2,000. I didn't get the 2,000 there. So this is going to be 0.05 times 0.95 divided by 2,000. So let's see, what do we get here? So this is going to be hold on here. 0.0625 minus 0.05. It's 0.0125 divided by the square root of let's see, that's divided by the square root of 0.05, 0.95 over 2,000. The z-score value I'm getting here is about 2.565, roughly. So now we're asked to state the results for a 1% level test. All right. So I'm going to go straight for the calculator now, and I'm just going to take the shortcut using the one prop z test built into the calculator. And the hypothesized proportion now is 5%. The x value, or the number of successes, as 125. Sample size is 2,000. Now the direction of extreme I've got to change to one-sided to the right. So I'll pick the greater than p naught and then calculate. Okay, so let's see. I had a decimal in the wrong place. Can happen. So one of the nice things about using the calculator, oh, look at this. I put in the wrong thing. I put in 20,000. Let me redo that. I got an error here. Let's see. Something didn't look right. All right, so let's go back. Well, I typed in 20,000. So let me get rid of one of those zeros. Sample size is 2,000, not 20,000. All right, one more time. All right, that looks better. So there's my p-value, about 0.5%. That's way less than 1%. We're going to reject, the decision here is going to be reject H naught. There's statistically significant evidence So we have statistically significant evidence that this city's unemployment rate is higher than 5%. Okay, so that's the end of Chapter 9, Part 1.